Okay, thanks for your patience, everyone. Let's get this webinar started. I'll first just start with a few housekeeping notes and introductions. Excuse me. My name is Braden McNeil. For those of you who don't know me, I'm the technical sales and marketing lead here at Aquanty. If anybody, after watching this webinar, is new to HydroGeoSphere, wants to learn more about this application and potential uses of HydroGeoSphere for water resources engineering, please feel free to reach out to me directly. My whole purpose here at Aquanty is basically to help people to explore HydroGeoSphere, provide frontline technical support, training, et cetera. I want to make a few small comments or just housekeeping notes regarding the presentation today. First of all, please note that this webinar is being recorded, and the recording, if you're not able to attend or sit through the whole presentation, the recording will be available on Aquanty's YouTube channel, perhaps later today or maybe tomorrow. So given that the meeting is being recorded, I'll ask everyone to keep themselves muted, and if you have questions for the presenters throughout the presentation, just place them in the chat and we'll have plenty of time towards the end of this webinar, hour-long webinar period for questions. Okay. With that, I'll make a couple of short introductions to our speakers today. Dr. Hugo Delottier is a groundwater hydrologist specializing in modeling flow and transport processes in heterogeneous, porous, and fractured media. Hugo earned his PhD in hydrogeology from the University of Bordeaux in France under the supervision of Professor Alexandre Priet, with a focus on model predictive uncertainty quantification and groundwater recharge processes. From 2018 to 2021, Hugo contributed to a major regional integrated surface and subsurface modeling project in Southern Quebec, Canada, alongside Dr. René Therrien, investigating the potential impacts of climate change on regional groundwater resources. And Dr. Therrien is, René Therrien here is a professor in the Department of Geology and Geological Engineering at the University of Laval. He received his bachelor's in geological engineering in 1986 and master's in geology, hydrogeology in 1988, both from Laval University, followed by his PhD in earth sciences in 1992 from the University of Waterloo. René was inducted as a Fellow of the Canadian Academy of Engineers in 2017 and Fellow Engineers Canada in 2020. In 2022, he received the Robert N. Farvolden Award from the Canadian chapter of the International Association of Hydrogeologists, recognizing his outstanding contributions to the disciplines of earth sciences and engineering, which emphasize the role and importance of groundwater. In 2022, René was appointed the director of the Quebec Water Management Research Centre, funded by the Quebec government. What René didn't mention in his bio that he provided is that he's also the original developer of HydroGeoSphere, and so probably has the longest history of using HydroGeoSphere for advanced water resources engineering and research compared to anyone in the whole world. Okay, with those introductions out of the way, I'll pass the mic over to Hugo to deliver our first little portion of the presentation, and then we'll be transferring the mic over to René a little bit later on.
Yeah, thanks, Braden. So hello, everyone. So yeah, my name is Hugo Delottier, and so what I will work today is what I will present today is a part of the work that I really developed and when I was in postdoctoral fellowship in Quebec with René. So during almost 4 years, 3 years and a half. Yeah. So I had the opportunity to come in Quebec and work on this. So that was it's also my pleasure to put one small picture of one of my numerous trips in the Southern Quebec region, which the region where we were talking about. So, but before to go further, I would like to acknowledge my colleagues that helped me during all this project. So Oliver Schilling, Nathan Young, and Daniel Paradis that also helped me during this whole project to set up this model and all the publications that came after. So yeah, so I will start to quickly make an overall presentation of the region. So today's talk, so me and René, it's really focused on, let's say, the South Quebec region. So the southern part of the Quebec region. So this region is no, it's in east. So as Quebec, it's east of Canada, south of Quebec here, and it's spanned between Montreal and Quebec mostly. And so it's a 30 up to 37,000 square kilometer region. So it's really large. And there is inside this whole region 8 catchments, hydrological catchments that are here represented by the black line that shows the water divided boundaries between the catchments. So there is these 8 catchments, and all of these catchments, the output of the outlet of these catchments is toward the St. Lawrence River. So it's all the water is coming from up to south to the north, and it ends up in the St. Lawrence River. So this region is really important because first it's mostly populated in Quebec. It's the south region that is mostly populated between Quebec and Montreal, all along the St. Lawrence River, and also there is in general 50-50 use of soil between agricultural industry and forest industry. So yeah, we can find cereals, oilseeds, and most of the arable zones, the zones that are used for agricultural production, are in the lowest part of the region, the low elevation part of the region, where it's mostly flat, and it's usually better for machineries, and it's drain swamps. So water in general, let's say, but groundwater also is mostly used for irrigation purposes, but also for drinking water production for some municipalities in all of these regions. So let's say in a climate change context, if we are expected to have less more prolonged period of dry, we, or at least this region, want to will mostly more be dependent on the groundwater to sustain the streams, the stream flows, the base flows, but also to keep these agricultural and productions as going. So the first objective of this study was to, in the climate change context, to evaluate the groundwater, let's say the regional groundwater vulnerability at this regional scale. And especially our goal was to evaluate the benefits of developing an integrated surface and groundwater model at that scale, to see how it can be useful and practical to evaluate this climate change impact on the groundwater availability. So it's really focused on the groundwater and on the base flows. So I will move directly to the presentation of the geological or hydrogeological context. So obviously, when we set up such an integrated model, we don't start from scratch. We have a good and well constrained idea of what is the conceptual model of the region. So here it's the in upper right of the corner of the presentation. It's the conceptual model and the lithostratigraphy units that we can find in the region. So as most of the region, let's say in Canada, we have this bedrock, which bedrock which is fractured at the beginning of the shallow depth, and less fractured at the deepest depth. And above this bedrock, you have a sequential accumulation of more recent deposits, tills, clay, and sand. And in these units, you have the till and the sand, which are mostly aquifers, which are much more permeable, and the clay is at some region, some part of the region is present and is confining the till units that is below and the sand units that is above. So here it's the conceptual model of the region, and so most of the groundwater recharge came from the southern part of the region, where it's more hilly and more high elevations pattern hills that we can find. It's called the Appalachian. It's Appalachian erosion where the most of the recharge occur, and the regional groundwater flow path comes from the south to the north, and the St. Lawrence River here play as a strong boundary condition where all the groundwater and surface water get out of the system. So in the left-hand part of this slide, you have the horizontal representation of the heterogeneity of these units. So you see that most of these units are lied in these low elevation, lowlands regions, which is called the St. Lawrence platform. And here at the right-hand side, you have also two additional cross sections that shows the lithostratigraphic units that are on top of the bedrock. So this really was the foundation, the basic of the developed integrated model. It's really what we use to populate the parameterization of the model in the subsurface. So, so as I said, it's we use an integrated surface and subsurface model, but our main purpose is to investigate the impact of climate change on groundwater. So we really want to focus the model on groundwater. So we could use HydroGeoSphere as a classic integrated model by using precipitations as input and let it rain on the model and see the partitioning between runoff and subsurface. But at that scale, the first principal issue is the computation time and the numerical stability of the model. So we try to find, as any good modeler do, let's say, an accurate representation of what matters in what you want to do with your model, which for us it's mainly base flow predictions. So groundwater that originates from and that exfiltrate in the streams. And so we kind of simplify our model by computing the infiltration, let's say the partitioning between runoff and infiltration outside of the integrated HydroGeoSphere model. So as I said, the model purpose is the regional simulation of base flow. So in that way, we compute infiltration partitioning externally, and we impose to HydroGeoSphere potential infiltration flux at the top of the subsurface flow domain. So in that sense, it's the left hand, the left sketch that you can see here. We have this potential infiltration flux that is imposed at the top of the subsurface domain, and which excessively reduce the compilation time because we don't simulate stream flow and fast flows that usually comes with stream flow. So we have a much more computationally efficient model, and we still have a really, let's say, a robust representation of the interaction between surface and subsurface, because we still have the model that is fully coupled between surface and subsurface, but we only simulate the groundwater pattern of the regional system. So we assume a simplification on recharge processes, mainly one-dimensional vertical processes, because we don't have interaction between cells to cells, and we don't have this runoff on the top of the model. So the model at that case, we obviously have to make let's say optimum size of cells we reach a level of refinement that was for us adequate to successfully reproduce and find the main streams, the main stream flow network in the regional system. And also in depth, because it's a 3D model, we have 200-meter depth. It was sufficient for us to simulate in the model the regional groundwater flux that matter, that can also get out of the system by these by the stream flow network. And so, as I said, the model forcing is the potential infiltration flux over that runs daily. So this simplified model, it's shown in the right hand side of the image. It's a bucket type model. It runs on daily stress periods over 4 years, and we from that model, which is discretized on a 25 square kilometer grid resolution, we build a representative seasonal cycle over 12 months, because our also again our originating purpose was to use the model to investigate climate change impact. So we want to build these 12 months of a representative seasonal cycle that is for us more consistent to evaluate the impact of climate change, but in a monthly basis over one representative seasonal cycle. So for parameterization, we use zones, as you said, the big zones of the lithostratigraphic units, but also pilot points for some parameters such as the bedrock hydraulic conductivity, the top bedrock hydraulic conductivity. And we have observations such as the computed base flow, which is perfect for us because it's also what we want to simulate with the model. It's the base flow. So here it's just an illustration of the average, the seasonal cycle that was computed from the infiltration bucket type model. So we use this infiltration flux over these 12 stress periods, so from September to August, to set up our transient simulation. So here we see that we have low flows and high flows. So low flows in the Southern Quebec region, it's mainly in winter due to snow accumulation, and high flows, it's also it's on the other side mostly in spring because we have the snow melt. So we have strong differences in flow between winter and spring and summer also after. But as you said, so and as I said, the infiltration flux then, so these fluxes, distributed fluxes, are applied at the top of the boundary, top of the subsurface flow domain for HydroGeoSphere. And so before using the model to make some forecast with the model, we want to make sure that our model reproduce quite well, or at least to identify the defect of the model in the regions. So we have a bunch of observations of hydraulic heads, but also on base flow. So we really focus the model calibration on base flow because this is what we want you wanted to predict with the model. So all along these 8 main catchments, we had several gauging stations with transient data. So from these stream flow data, we computed the base flow, so which was extracted with a particle filter approach. So we computed the base flow at each of these gauging stations to have the correct observations to reproduce, and then we calibrate the model. So instead of using one set of model parameters to calibrate the model, we choose to estimate the best model parameter sets while also estimating the uncertainty analysis, the uncertainty that came with the parameter estimation process, because with such a large-scale model, highly parameterized, there is obviously some uncertainties that are originated just because we don't have enough information to constrain the parameters that we have in the model. So we wanted to, at that scale, with an integrated model, test the iterative ensemble smoother that is perfectly suited for such model, for such complex model that takes time to run. And so we successfully use higher iterative ensemble smoother to generate an ensemble of plausible models that are all more or less calibrated, that are all able to simulate, to reproduce the observed base flow at all the gauging stations that we have in the region. And with these models, we were able to then stimulate the forecast for the groundwater level and the base flow in the climate change context, and also for the subsequent analysis that I will present just thereafter. So here it's just a quick, really resume and summary of the model setup. If you want to have a more comprehensive information about the model setup and the calibration and the uncertainty analysis, you have to find this the first paper that I published in 2021 with René about this model setup. So now I will jump right into the simulations that we did with this model. So as I say, we were first focused on using this model in climate change context. So then when we had all of these this posterior ensemble of calibrated models, we used climate scenarios, simulations from climate scenarios, and we impose these simulations in the model. So here it's just, so it's not the main topic of this talk, but I just quickly present what we did just in that direction. So we had a reference period. So as any hydroclimatic simulations, we always have reference period and mid and end century period, and we want to evaluate the impact of this climate change along this period compared to reference period. So we had a range of different climatic models and scenarios. And what we saw here is just the data, the simulated data that we had from the climate models scenarios, and we had a little bit increase of precipitations, but not. So it's the yearly average. It's the yearly average between all the models and the scenarios. So a bit increase in precipitations, but what was really more evident was to see the larger increase in temperature in the mid and in the end century. So yeah, that was the main data forcing for the climate change simulations, the hydroclimatic simulations. What I want really to show here is just one of the output that we had after the hydroclimatic simulations. So here in this slide, you see for all the 8 catchments and for the whole the one representative seasonal cycle that range from September on the right, on the left, to August on the right. You have for the 3 period, the reference period, the mid-century period, and the end-century period, the model-based uncertainty. So let's say the uncertainty that comes from the model itself, not from the climatic scenarios. And I really, what was really interesting in this figure was to see, as long as we move to the mid and end century, the uncertainty that originates from the model was reduced, and the uncertainty that originates from the boundary condition from the climate forcings increased. So in the end, our uncertainty that came directly from the model, let's say from the non-uniqueness of the inverse problem, is more important in near the period that we calibrate the model, but not as important when we look at really long time periods, because at the end it's much more the forcing that is important, and that play much more that have much more impact on the model simulations. So that was all that I wanted to present on that side. And then on the other side, I want now to jump right into the main topic of this talk. It was to really investigate the impact of surface water and groundwater interaction for simulated for simulation of the groundwater levels at the regional scale. So once we had this model, this fully integrated model, but first with infiltration flux, we wanted to investigate to what would be the impact, what is the impact at that scale, at the regional scale, of explicitly simulating the groundwater infiltration and the groundwater exfiltration and re-infiltration. Because as I said, we don't have direct infiltration because we don't have runoff infiltration partitioning in the model, but we only have groundwater that can first exfiltrate and goes into the surface domain, and then potentially re-infiltrate after. And there is these two-way interactions all along all in the model. So it's in that way. For surface water groundwater interactions, it's a fully coupled model. So it's a two-way integrated model when we have feedback explicitly simulated in the model. So we can do that because HydroGeoSphere is at the basic, at the core, an integrated model with this feedback considered. So to investigate what would be the impact of not considering this feedback, omitting this feedback, it's on the right-hand side of the sketch. So it's investigating what would be the impact of this two-way interaction between this one-way interaction. So not considering the potential re-infiltration after we have groundwater exfiltration. So it's what I call what is called in the literature in general a one-way groundwater model, where groundwater can only exfiltrate from the subsurface to the surface flow domain, and then it is removed to the general water balance. And it was important for us because in the literature in general, there is no such, or it's difficult to find such information. And it's completely consistent because at that scale, the time spent to build a model and to calibrate it and to run some simulations, it's quite an important step. Huh? So developing multiple models with different philosophy, different approaches, it's usually not available. And when it's available, usually it's not the same modeling code, and it's not the same model meshes, it's not the same boundary conditions, the same forcings. So usually when there is differences between these kind of approaches, the strict impact of the conceptualization of the surface water groundwater interactions, either the two-way or the one-way interaction, is not it's not easy to find, because it's also mixed in between in other differences. Yeah. So what we did is that from the two-way integrated model, we transformed this model to a one-way groundwater model by just putting head boundary conditions at the overland flow domain, which were equal to the node's elevation of on the overland flow domain. So in that way, we were able to simulate groundwater exfiltration, but not the re-infiltration thereafter, because in that way we just lose water that exfiltrates from the groundwater and remove the water from the regional water balance. So with one single model with the same parameters, mesh, boundary condition, and we just have two different conceptualization of the groundwater and surface water interactions, and we can investigate the impact of this simplification. So what we did is that once we had these two models, we subtracted the model simulations from one model to another, and then we had explicitly the differences that originate from the conceptualization of the groundwater interactions. So the model, as I presented before, is transient. So we have transient monthly simulations. So we have differences between the model in transient. So what we saw is that in general, the integrated model, when you have these two-way interactions, leads to higher water table elevations than the one-way interaction. And in general, the differences which were much more important in low elevation, lowlands elevations. And we also had differences in between the transient period with much more differences in low flow conditions and high flow conditions. And so when we look at the exchange fluxes, it's also explained the differences between the two. So when we remove the reinfiltration part of the model, so on the upper side here, we remove a lot of water from the system, and in the end, all the water that can potentially reinfiltrate is removed, and so the groundwater levels decreases, and so the main difference is that when we remove this feedback, the one-way groundwater model had much more lower groundwater elevations. And so, yeah, we see that omitting this feedback clearly remove an important part of the catchment hydrology. And this can also, so significantly, we can significantly overestimate the depth to groundwater with one-way coupling schemes. So, and then at that point, we also run a sensitivity analysis to see what would be the impact of neglecting this feedback. But in terms of the sensitivity of hydraulic heads to the model parameters, which for us it was the hydraulic conductivity of the top bedrock units. So we used a sensitivity analysis, and we saw that the one-way generally was more sensitive to the two-way integrated model. So removing these feedback processes from the system usually increase the sensitivity of the model parameters to hydraulic heads. So the model is much more, let's say, in that sense, easy to calibrate, but also much more depend on the parameters that the value of the parameters that we put in the model in the other way. And the differences was not significant between lowlands area and uplands area. So yeah, try to conclude quickly. So as I said, neglecting these feedback processes potentially leads to lower water table elevations, and we observe that especially in lowland regions, so at low elevation regions, and we attribute that because in that part of the region, the groundwater is mostly connected to surface water. And we also see a stronger difference in low flow periods. And so yeah, so as I say, when we don't consider this feedback process, we can have a much more sensitive model to hydraulic heads, maybe easy to calibrate, but it's also must depend on the initial parameter value that we put in the model. So to on the other hand, to have the same to compensate this bias. And yes, so this was the more regional investigation of my part, and now I will let the floor to René for a more local scale assessment of the groundwater vulnerability. Thanks.
Hopefully you all see my screen now. So thanks, Hugo, for this first presentation. And I guess the advertisement was not totally correct, my fault, because I will not be talking about the southwestern part of the province of Quebec. The study area is just north of it, to the northeast. It's the Quebec City area, and we are looking at assessing the vulnerability of the main surface water intake for the city. And I just want to make a brief comment on what Hugo presented. The work he did was, well, we did together was funded by the Quebec Ministry of the Environment. And it's really, it was really focused on water resources management because the motivation for the ministry is that they have a surface flow model that they're using in operational mode. They're using to forecast, say, 5 to 7 day periods. And the surface flow model called HydroGel is doing a really good job for the high flow conditions. For example, flooding in the spring because of snowmelt, or very, very strong rain events in the summer or in the fall. But it's doing quite poorly for low flow conditions, recession, either in the winter or in the summer. And for the ministry, the low flows are of high concern because of course, impact on ecosystems, but also in the southern part of Quebec that Hugo has presented, lots of municipalities take their drinking water from rivers. And the low flows mean that, well, you might have shortages of water, and also the water quality changes. So that's why they were really interested in having us using HydroGeoSphere to simulate what happens in this region. And we focused really on the low flow conditions and the base flow. So hopefully the ministry will adopt our approach to look at these long-term forecasts of flow conditions, especially the low flow conditions. So here we have a project that we've been doing for the last several years, and I should acknowledge right away the co-authors Benjamin Fro, who's in attendance at the moment. Benjamin is doing a PhD with me at Laval, Laura Gattel and Johan Tremblay, and Hugo also contributed to the modeling effort here. And if you have any specific questions, probably I should forward those questions to Benjamin or Laura, because what I'm showing here is really the work that they did. They did the hard work, and I'm just presenting a summary of the project. And the what I'm presenting is going to be really an overview. I don't want to go into any detail, but the focus is to show how our type of modeling can support water management decisions. And again, this was funded by the, in collaboration with Quebec City, and they're really interested in the long-term management of the water resources. So as far as vulnerability goes, or let's say wellhead protection, well, it's quite established now. We have methodologies for like the wellhead protection, where we're using pumping wells to extract groundwater. This is an example of the current regulation in Quebec. So there's a pumping well. I'll take my, oops, sorry. Let me go back. So we have a pumping well, and in Quebec we define different zones: an immediate zone, which is a 30-meter diameter around the well. Then intermediate corresponds to the life expectancy of bacteria. It's 200 days travel time to the well. Intermediate, it's virus life expectancy, 550 days, and then the whole catchment. So these areas can be defined with simple analytical models or numerical models. But when your drinking water is river water, there's really less defined or less defined methodology to look at the vulnerability and potential sources of contamination. So in Quebec, we have recent regulations. There are more our guidelines, where the Ministry of the Environment has asked the municipalities to define the vulnerability basically by looking at various areas. So the water intake in the river is here. The first area in red is the immediate area, which is some distance upstream and downstream from the intake and a corridor along both sides of the stream. There's an intermediate area in orange here, which goes further upstream and also goes deeper along the sides of the stream. And basically, municipalities have to look at, okay, what are the potential sources of contamination that could lead to contamination of the water intake, so contamination in those areas. And then they also define the entire catchment. And municipalities don't have to do very detailed hydrogeological studies for the entire catchment, but it's more identification of potential sources of contaminants. And Our partner, the city of Quebec, they wanted to go much further. They're planning long-term for the water resources. So we had been working with them for quite some time, and they were aware that, well, if you have water in the river, it's mostly groundwater, so we have to look at the groundwater system. So we got funding to basically develop a model. In the end, it was a model, but to characterize the hydro system, groundwater and surface water for the entire catchment, and also to develop a model to do some different types of forecasting. So this is the catchment. Quebec City is right here. It's in the northeastern Canada. It's just north of the region that Hugo presented. So the catchment, this is a map of Quebec City is just to the south. The catchment is shown here by this yellow star, the intake. It's in the river, the St. Charles River. And that's the old catchment of the water, the drinking water intake. So the area is 350 square kilometers, which is less than 10% of what Hugo was showed the previous presentation. The water is a source of water for 300,000 people, and the average withdrawal rate is more than 100 million liters per day. And in the low flow periods, especially in the summer, withdrawals can reach 92% of the total river flow at that location. So there's, for the city managers, there's really long-term concerns with water quality, water quantity, and as well as climate variability. What happens if we have warmer, drier summers? Are we going to have to look at other potential sources of drinking water or additional sources of drinking water? So we, as part of this project, we installed a network of gauging stations and observation wells that were spread all over the catchment. You see here with the various dots, the purple dots and the red triangles. So that allowed to get time series of surface flow rates as well as hydraulic heads. We had already compiled all the existing information on the geology, the subsurface geology, as well as land use. The land use is shown here, and this is used to inform the model to define some parameters for the surface water flow, for example, or the exchange between surface and subsurface. And this is a simplified representation. Actually, it's much more complex than that, but for the purpose of simulations, we only used 4 different types of land use: anthropic or urban, forested, just water bodies as well, and wetlands. And similar to what Hugo has shown, the geology is typical of what we have in Southern Quebec. We have bedrock. In this case, it's Precambrian rock, overlain by glacial deposits. And this is a map of the various surface deposits, and the bedrock is shown in red. And again, this was fairly simplified as far as the glacial deposits, because we wanted to have a limited number of hydro units in our model. We had access to thousands of well logs that were carefully analyzed to look at the thickness of the various sediments on top of bedrock. So the map here shows the thickness of the glacial deposits here on the left. And here on the right, we have the thickness of what we considered as aquifer material. So there's some very permeable sand and gravel units in the catchment that are not all over the catchment. They're not spread. You see they're sparsely distributed, and they represent locally sources of groundwater. And I should just point out here, this area here, you see the name Shannon, this area here with the thicker deposits, it's basically sand and gravel. That's where we have this big TC contamination problem. It's an army-based, the Valcartier-based, and there's been a very widespread contamination by TC that dates back to the Second World War. So Lova and Benjamin basically developed a HydroGeoSphere model, fully coupled 2D surface and 3D surface model, subsurface model for the catchment. I don't have all the details of of the extent of the model in terms of number of nodes and unknowns, because there's been several iterations. They had to refine the model to represent with more accuracy the topography, because they calibrated the model to surface flows at various locations at the gauging stations. But they used like the typical approach, basically use the existing data, topography, geology, land use to populate the different parameters that are used in HydroGeoSphere. The forcing is the daily weather forecast. And the outputs, of course, are river flow rates, hydraulic heads. And we also looked at groundwater recharge, variations in the amount of water storage, water stored in the system, the travel times. And again, this was done in collaboration with non-hydrogeologists who work for the city, who are like the water managers for the city. So we wanted as well to extract some results that were of interest to them, as well as to allow them to better understand the dynamics of the system. So without going into any detail, we had, Laura and Benjamin worked very hard to calibrate the model, to stream flow measured at the various gauging stations. This is an example here. So they had a calibration period and a validation period, as well as hydraulic heads measured at the several observation wells. And in general, the model performed really well, perhaps in some locations not as well, but in general, for all the observation time series we had, they really had a good calibration of the model. Just a few very general results. And again, this is the type of results that we show to our partners to make them understand the system. Something that is quite typical in our climate, say in Southern Quebec, ground is driven by topography. So the water table is typically not very deep. It follows the surface topography. So we have a map here with the blues are the higher values to the north, and the groundwater typically flows from the northern part to the southern part of the catchment. And again, the intake is here, this yellow star. And the model reproduces the seasonal variations of water table elevation. And this is a result of interest for our partner, because they are, as the Quebec Ministry of the Environment, they are quite concerned with the low flows in the summer. And these are variations from mean values at the several observation wells for the period 2018-2022. And typically, the water table elevations are lower in winter. They go up in the spring, then they decrease again in the summer, and they go up in the fall. So these seasonal variations, again, are of great interest for the water planners in the city. And I should say that they're not only concerned with the low flows, but there's flooding events as well on the catchment. So our modeling approach is of further interest for them. So we show something that we'll kind of all intuitively know, but when you talk to people working at the city or elsewhere, they really don't see that groundwater is the main contributor to surface water. So we show here baseflow contribution at the intake. It goes from 95% in winter to 60% in the spring, and close or above to 80% in the summer and in the fall. So baseflow provides 74% of the annual mean stream flow, and up to 95% in winter. And that's an eye opener for a lot of people, because traditionally in the past, when people were trying to manage the surface water intake, they were only looking at the surface drainage network. Nobody looked at groundwater at all. So now we show that, well, groundwater is critical for the surface water intake, and we have to account for that. And our partners are now very convinced of that. One result we can extract is our annual recharge. This is a map here. Again, without going into much detail, it just shows that it's quite heterogeneous, related to surface topography, related to the surface material, as well as the permeability of the subsurface. I will skip that one because I think I don't want to run too late. We don't have a methodology that can tell us, well, provide directly a vulnerability index for the surface water intake. So We still are exploring various ways to illustrate that, or at least to provide the information to our partners. One thing that we use is fairly recent addition to HydroGeoSphere as travel time capabilities. And Benjamin did that, and he released basically particles, so it's particle tracking. He released particles at the water table, and then he releases them uniformly distributed over the whole catchment, and he computes the time for the particle to leave the system, basically to exfiltrate. So the travel time is greater than 17 years for 50% of all particles, and you have a distribution percentage of all particles as a function of travel time. And you get some very long travel times because some areas, the water enters the bedrock, which is very low hydraulic conductivity, but it gives an indication of travel times to surface water, either a lake or a stream. So this map here gives the indication with the blue areas showing the lower or shorter travel times. Looking at vulnerability, of course, we computed the drastic index, which is quite standard. Was not computed with HGS, but just outside of HGS. So we end up with 75% of the area is vulnerable with an index greater than 100. 20% is highly vulnerable. And there's a spatial distribution of the different vulnerabilities over the system, over the catchment, which are shown here. And trying to come up with a way to present these results to our partner, we combine the drastic index and the travel time to end up with a map shown here on the right. Basically, the vulnerability, we distinguish between highly vulnerable and vulnerable based on the drastic index. And the time scale, short term is a travel time less than 5 years, and medium term is a travel time less than 20 years. So outside of that, we don't consider that vulnerability is very high. So we end up with this conclusion that 24% of the watershed is vulnerable, and 10% of the watershed is highly vulnerable in the short term, which would be on this color map, this dark brown color. It's this color here at the top, highly vulnerable in the short term. So in terms of land planning, or at least making sure that there's not potential sources of contamination that can enter the groundwater system and reach the river, the stream, these would be the areas to focus on. And again, this is quite valuable information for our partner. And very quickly, Benjamin is working on this right now using the hydraulic mixing cell option of HGS to look at the various fractions of water that are present in the stream. Basically, what the HMC does is at the start of a simulation, you tag the water. So the water can be rainwater, water in the aquifer, water in a different unit. And then as the simulation progresses, these different fractions move into the system, and you can see how the water evolves. What is the composition of the water in, for example, the stream? And this is shown here by the various colors. So this would be a variation of the fraction of water that enters the stream as a function of time. Again, I'm not going into the details, but this provides additional information of where is the water coming from when you're looking at a specific location. And very quickly, that's also ongoing, looking at scenarios of land use. This is of great interest for our partner because we are in an urban area. There's urban development, especially towards the north. How will that change the system? So we have different scenarios. Some are realistic, some are not all that realistic for urban development in the catchment, and to see how does the system respond, how does recharge changes, the flow rates changes, and so on. And of course, Hugo mentioned that for the other region, climate change is of great interest. So Benjamin got some scenarios from, we have a consortium in Quebec called Uranus, who they're doing climate research, but also climate services. They're providing scenarios if we ask them. So we have scenarios for the period 2071, well, actually more than 2071. You see the scenarios for the maximum daily temperature here on the top left, minimum daily temperatures and precipitations. And you see temperatures are predicted to go up, precipitations slightly go up, but it's not linear in the sense that, for example, in summer, temperature might go up, will go up, there will be more evapotranspiration, less water, and precipitation might go up or might go down, and the seasonality is also quite important. So that's something that we can look at with HydroGeoSphere. And finally, quickly, conclusion and outlook. I think this is a project that shows how we can use the model to help people who are responsible for managing water resources in the catchment. And in this case, it's the city personnel. They're actually also responsible for land use, allowing permits for constructions and, for example, urban development. So they're quite interested in looking at what will be the impact on the system. The water intake is very precious. They want to preserve the quality as well as the quantity of the water in the river. So we, I guess we've shown to them, we've demonstrated that the long-term management of water resources requires an integrated approach. You cannot just look at surface water. It has to be surface water and groundwater. The groundwater component is very important. And of course, yes, we demonstrate, and we're quite convinced that the HydroGeoSphere is an ideal tool to look at these systems and help water managers. So I will conclude here. Hopefully, I've not gone too long.
Thank you very much, René, and Hugo as well. Great presentations. If you're both free, I think we can maybe stick around for a few extra minutes just to address a couple of the questions that have come in.
Sure.
Hugo, there was actually a couple of people who had asked how the daily infiltration rates were calculated, and specifically the spatial distribution. Did you use a specific software for that? But basically, how'd you approach that?
Yeah, so it's really presented in the paper that present the model setup. But what I use is the bucket type model that is spatially distributed and transient. So it's called ModQ. It's a model that I started develop this model during my PhD, and then I fully finished to develop this model for this for this project. So yes, it's a Python based. It's all in Python. So what I had is I read the input with Python, and I generate the partitioning between runoff and filtration with this model. We also have snow accumulation and melting processes in this model, and yeah, so it's yeah.
Excellent. There was a question that I tried to respond to a little bit about whether there have been any papers or studies that compared the results of HydroGeoSphere with other uncoupled programs. Now, I dropped a response to that in the chat and referenced 3 different papers that provide some comparison, but obviously comparing different models is difficult because of the different governing equations, different conceptualizations of flow. But I guess open question to both of you. Do you have any comments about, basically comparisons of HGS to other either coupled, tightly coupled, loosely coupled hydrologic models?
Yeah, so here it was not really to compare SGS to another type of models. It's just to compare. It was much more to focus the comparison of on what is the impact of these feedback between surface and subsurface for the regional groundwater simulation. And in the literature, you can find some comparisons between different type of models. So these are different grids and equations and parameters at let's say a field scale. But at regional scale, it's almost it was not available in the literature simply because in general it's really long, and it's to set up such a regional scale model. So if you want to develop 2 different regional scale model, yeah, that's almost that's really challenging. I don't know, René, if you have something to add.
Yeah, this is a very good question, because we had this discussion with Hugo, and Oliver Schilling also worked on that paper. Like one question that a model might ask him or herself very often, okay, I've got this catchment, I want to develop a model for. It could be a very large scale or smaller scale. Like, do I need a fully coupled surface groundwater flow model? Because no, it's challenging to use. You need a lot of data. Can I get away with a simplified approach, groundwater flow only model? So that's the type of question that comes up quite often. And of course, I'll say we are probably very biased because we are using HydroGeoSphere. We know it's a great tool, but we wanted to investigate this question. What if you want to make the model simpler, say run faster by not representing some processes? And that's why we stuck to only HydroGeoSphere. We said, okay, if we compare HydroGeoSphere with a different numerical model, then the differences we'll see might be caused by different discretization. The equations are not exactly the same. The numerical methods are not exactly the same. So how do you distinguish between these differences and the differences in the process representation? And we decided to use HydroGeoSphere, like exactly the same grid, exactly the same parameters. And Hugo has shown that just the coupling of the surface, it's one way or two way. So that's the only difference. And then we can demonstrate, oh, what is the impact of representing this two-way coupling, or simplifying it by representing only one way. Only water can exit, groundwater exits the system and then cannot re-infiltrate. And Hugo has shown the impact. So in that sense, that's why we only wanted to remain with HydroGeoSphere and not start comparing other models. But there's I see Ed is in the room. Ed has taken part in some model intercomparison, coupled surface water, groundwater flow models, but the comparison was limited to very, very simple cases, almost hypothetical cases, not real cases, where it becomes quite difficult. And I will add another thing that Hugo has also shown and demonstrated during his work, is that let's say you have a representation of the subsurface geology. You might have that into a GIS database. And then typically when you generate a mesh in 3D, you will interpolate that information onto your mesh. Well, what if the mesh size, the mesh geometry is different between two separate models? Like, your geology will not even be exactly the same. So that's another source of difference between the modeling, the different models.
Thanks for making those comments. I think we'll maybe take two more simple, pretty quick questions. The first one for Hugo. Somebody asked what boundary condition was used to apply the vertical flux in your model. I responded probably just the flux boundary condition in HGS and provided a screenshot. Is that correct?
Yeah. It was a flux boundary condition applied at the top of the subsurface flow domain.
Yeah, so in HydroGeoSphere, you're able to apply both time and spatially varying boundary conditions for almost any boundary just by applying a time series of different raster files.
Yeah.
And a question now for you, René. Maybe slightly difficult for you to answer because I know that this research was primarily done by Benjamin, but do you know what the weights were used, what weights were used for that drastic method? I'm not too familiar with the method myself, so I can't really elaborate on the question more.
What weights were used? My first answer would be that I think they basically follow the drastic methodology with the different, like each letter indicates one parameter, but I don't have the details. I could probably find that out, or I know Benjamin is in the room. Perhaps he can quickly answer. Otherwise, we can provide an answer later on.
There you go. Benjamin actually just provided a link there in the chat to follow up on that. And one more last question just came in. I think I can answer myself. Do you use HGS and GMS, and do you have a specific computer program for meshing? Now, we have recently partnered with Aquaveo. It is now possible to build HydroGeoSphere models directly in the GMS interface, which is developed by Aquaveo. However, it's still pretty this is still a relatively new development, and I believe a lot of this research actually predates the availability of that interface within GMS. So I think I can speak for both René and Hugo and any of the project collaborators for these particular presentations that GMS was not involved. And with respect to a specific computer program for building the model mesh, what Aquanty has always, or for many, many years now, recommended is a program called AlgoMesh. It's developed by a company in Australia named HydroAlgorithmics, and it really is the best program on the market, in our opinion, for generating highly optimized triangular element meshes. So
Yeah, I might just mention quickly that Hugo is a wizard at developing all kinds of Python scripts to go extract data from various databases and then put those in the HDS format. So he was very efficient at that.
Yeah. But in the residual model, yes, the latest version was the mesh was developed by AlgoMesh in the end. At the beginning, we used a Python-based script with Triangle. But yeah, I agree with you, Brayden, that this AlgoMesh is really powerful to have really strong, good meshes. Yeah.
If anybody, again, is interested in HydroGeoSphere, GMS, or AlgoMesh, feel free to reach out to me. I did put my email address in the chat there. Aquanty is authorized reseller of both AlgoMesh and GMS, and of course, we're the primary developers and sole distributors of HydroGeoSphere. So if anybody is interested in leveraging any of these software packages for their own research, please feel free to reach out to me. I would be more than happy to have a chat. I don't see any other questions in the chat, so I'll just thank Hugo and René for your time today. Great presentations, and hopefully we'll be able to reconnect with other webinars again in the future.
Well, thanks a lot, Brayden, for organizing, and thanks to everyone for attending.
Okay. Yeah. Thanks, everyone. Have a great day.
Bye.
Bye.